Hi there, welcome to a quick tutorial about enthalpy and stoichiometry. So I'm going to do one of the questions coming from worksheet 16.3, which was titled enthalpy stoichiometry. So one of the things you learned in grade 11, just to recap quickly, was that mole ratios can be used to determine the moles of a product produced, or any ratio in the substance, the volumes of gases reacting and produced, or the amount of energy absorbed and released. Okay, so mole ratios were very powerful. All right, and they come from the balanced chemical equation. So they can be used to determine amounts in moles, volumes of gases, and energy. So we'll start off with the balanced chemical reaction, and then we'll talk about what a mole ratio is and how it relates to energy changes and enthalpy specifically. So I'll start off with number 1 from the worksheet here. So to follow with the balanced chemical equation, sulfur plus elemental oxygen producing sulfur trioxide, and there's an energy change of negative 791.4 kilojoules associated with that. So there's our balanced equation, and don't forget the coefficients in front tell us what the mole ratios are. So the question's asking us for the amount of heat released, which is delta H, when 6.44 grams of sulfur reacts with excess O2, according to the following situation. So because oxygen's excess, it means sulfur is the limiting reactant, and there is 6.44 grams of that. Now, to work with mole ratios, we need to know the molar mass of the substances. So for sulfur, if we go to our periodic table, we're told its mass, that's its weight amount, is 6.44 grams. And as per the periodic table, its molar mass is 32.07 grams per mole. All right. Now, in grade 11, when you did with stoichiometry, you would have looked at either a product or a reactant, determine the number of moles, set up a mole ratio, and been done with it. This time, though, I'm telling you, we can do that with the amount of energy. Okay, so we're going to set up our ratios a little bit differently here. All right, so this is all the information that we need, and we're being asked to find delta H of this reaction. So the value that we're given, kind of with the reaction here, okay, and these black arrows mean nothing, but that means for this reaction involving 2 moles of sulfur, 791.4 kilojoules of energy gets released. So we can start it off like this. 2 moles of sulfur, actually, we're going to write that on the bottom. Okay, the change in enthalpy is equal to negative 791.4 kilojoules for every 2 moles of sulfur. We'll just get rid of that there. So that's our first ratio, all right? And really, we're setting up a molar enthalpy problem here because the molar enthalpy won't change. Now what we're saying is, what is the amount of energy released when not 2 moles of sulfur reacts? Okay, so we're going to keep them in the same ratio of each other because the molar enthalpy is a property of the element. Whatever it is, it won't change. Okay, so using the ratios here, if we determine the number of moles of sulfur, okay, we can set up a mole ratio with the energy, and then we can solve it from there. All right, because really when we solve this first fraction, that gives us the value, and this is for combustion, right, of some number, and that has to be true of sulfur in all amounts throughout this reaction. So let's start off with this here. Just kind of zoom out. So we'll call this part A. The number of moles is the mass divided by the molar mass. So we're told 6.44 grams reacts, and 32.07 grams are in every mole of sulfur. So that means here, with the 6.44 grams we were given divided by the molar mass, we have with us 0.021 moles of sulfur. All right? Now you might be thinking, well, why are there 2 amounts of moles? Well, the first one is based off the coefficient, right? And the second one is based off the amount that's actually reacting. So now we can substitute this amount in here. And the key is that once you can find the molar enthalpy, okay, which is what we do in the first part. It has to be consistent. So what we'll say is, now use ratio to find delta H. So we'll say negative 791.4 kilojoules divided by 2 moles of sulfur. And we chose sulfur here because that's the amount we're given. Has to be equal to the molar enthalpy change, which is what we're trying to find, divided by 0.21 moles of sulfur. Okay, so this is your mole ratio. It looks a little bit different than maybe what you remember from grade 11, but it's still comparing the number of moles, right, to a property that can be determined. So if we cross multiply and isolate now, let's say delta H, okay, and pay attention to the units here. So we'll take all of this, 791.4 times 0.201 divided by 2. So if you look at this, you say, okay, 2 moles of sulfur can release 791 kilojoules. But we don't have 2 moles. We have 1/10 of that. So 1/10 of the energy should be released. And when I punch that in, or about 1/10, my answer is 79.5 kilojoules. And it's negative. Now, does that make sense? Yeah, that's about 1/10 of it. So we can say, therefore, go here, 6.44 grams of sulfur will release 79.5 kilojoules, and the release acts as the negative sign here, of energy during the reaction with oxygen. All right. Now, we'll zoom out, and that's it for this question here. And anytime we work with reactions, it's important to remember the mole ratio. But keep in mind that once you find the molar enthalpy, which is delta HR, okay, H divided by the number of moles, that's constant for the same element. Okay, so if you find it once, you can use that, which is essentially what we did with our mole ratio. Because what we said is that delta HR equals delta HR, right? And then we set these two equations equal to each other. So one is using the coefficients from the reaction and the energy change from the reactant, and the other uses the mass data or the given amount to find the amount of energy. Okay, so hopefully that helps in general. Leave a full screen there. All right, and this can apply in a bunch of different scenarios. It's important for us just to know that we can use mole ratios, like it says in the top right corner, to find amounts, volumes, and energy.